Once we're satisfied with the design specification, our next concern are the set of processes used to transform the material into our final product. That's what we'll be looking at today. So from the design perspective, we have this extremely idealized view or theoretical idea of what the product should look like after manufacturing. And then when we look at our manufacturing perspective in terms of our system, what we're concerned about are the set of processes that we're going to use to transform our material into that final product. Each part that we produce is one realization of the product, and the combination of the set of processes produce a unique form for the product in terms of its features, as we've seen in the design specification. So we should begin to ask ourselves some questions. You understand something about manufacturing processes from 248. So you wonder, well, how will this process affect our product in terms of the shape, the orientation, and the position of various features in that product? What we've said from the beginning is that deviations will occur from the nominal, and we expect that to happen. So you observe material inputs from previous processes or the raw material, and then we have some type of transformation that occurs where one or more features are added, and or we change the material properties in some way. After we go through a process, then we ask ourselves this question: did you obtain the change, the delta, that you intended to produce after going through the process? If you did, then you're going to say, yes, we continue to have a good part in terms of conforming to the specifications, or no, we have scrap that must be dealt with in some manner. So if we look at our process from a modeling point of view, and here we have an individual process that is transforming material into what we think is good product. The contents of the process would correspond to some type of manufacturing process that transforms geometry and or material. The good product becomes work in process. So the WIP represents product that proceeds on to the next process. The material entering this process begins in its initial state and then ends up in a different state once it has been processed successfully. Now the downside here is what happens when things go wrong. So we have certain deviations that occur during the process, and as a result of that, some of the product will result in scrap. Now we have to be very specific about how we're defining scrap here, because various institutions will describe that in different ways. What I'm referring to when I refer to scrap is that we were not successful in achieving the transformation that we were trying to produce in this process. So the first pass through the process was unsuccessful, and that we'll consider to be scrap. Once we have a part that comes through that process that is not acceptable, then we have to make a decision. That decision is, can we rework that particular part, or will it enter directly into the waste stream? And now we have to be specific about what we mean by waste. By waste, we're referring to material that will either be salvaged, in other words, recycled, or it's going to enter the waste stream in terms of a landfill or other types of waste remediation. Some of that waste is coming directly from the process. For instance, if we're cutting pieces out of a steel plate, we will not utilize the entire steel plate. So some of that material will end up in waste. The other material will either end up in our work in process going on to the next process, or it will be scrap that will either end up again in waste or in rework. Once we make a decision to go to rework, What we're trying to do here is restore that particular component to its intended level. And if we're successful, then it will re-enter work in process and go on to the next process in our system. If we're not successful, then it will enter into the waste stream, and we will have to deal with that according to whatever the material is. Now, you'll note this vector here indicates the flow of material potentially entering into rework, and this would indicate that we're adding additional material. For instance, if we are replacing a component on a circuit board, we would have to remove the original component. That would enter the waste stream, and then we would add another component, and that would represent the rework, and then we would enter into the next process if we were successful. So here's a fundamental question about our model. Again, this model will be the basis of every single process in our manufacturing system, so it's important to understand what is happening in this model. So we ask the question, and you'll be doing that in your project when you do your time studies, where are we adding value? Now this term value, what does that really mean? Well, what it boils down to is, have we changed something about our system in terms of the individual components going into the final product? And by value, we mean some delta. If we're going through a process and we change the geometry or we change the material properties, then we say we're adding value. And so that should occur in the process. Now, what happens if we create scrap here? That indicates that we did not produce the value that we were intended to produce. And therefore, we enter into rework. And at this stage, what we're trying to do is create this delta that will bring us back to the intended value that we wanted to produce in our process. So it turns out that in our process and in rework, we are actually creating value for our product. Now, you might hear people say that rework does not add value, but that is incorrect. We are not commenting on whether it's a good idea to do rework. We're only commenting on the delta that that particular process is producing in terms of geometry and material properties. So in both cases, we have value being produced by the process and value being produced by rework. Later on, we'll talk about the notion of rework and perhaps when it should be done and when it should not be done. Can we add negative value? So that would be another important question. Well, positive value implies that we're getting the change that we intended. A negative value means that we are somehow diminishing the product characteristics. And therefore, it's possible to add both positive and negative value. Clearly, you do not want a manufacturing system that creates negative value. Otherwise, you'll be out of business. So this is the basic model that we'll be looking at. From a material balance point of view, you are putting some amount of material into your process. And that is indicated by Q plus W, where Q is the quantity of material that is required for the part. So that's what's going to end up with the customer. And then W is the waste quantity per part. And that waste quantity will enter the waste stream directly. So we come in with Q plus W. After the process, we have just Q. Now we're only looking at one process right now. You can imagine a sequence of processes. Q may increase or decrease as we're aggregating or removing material for this product. And here we have some question marks as to what's happening with this kind of material. An important parameter of your manufacturing process is what we call the scrap rate. And that is the fraction of parts that will be defective after we leave the process. So as you can see here, if we multiply S times Q, that will represent all the parts that we consider to be defective. And once we leave the process, some of those parts will enter the waste stream directly. The ones that we can rework will enter rework. And then, of course, some of those will end up being work in process, some of those will end up in the waste stream. So we have these question marks. We know we have W because we are throwing away material potentially. Now, of course, W could be 0 depending upon the process. And here we know we have 1 minus S, which represents good parts, times Q in terms of material. And then the question mark here refers to how much additional material or additional parts are passing through rework and will be added to our work in process. So this is basic material balance. Of course, it's a zero-sum game. Everything has to add up. Otherwise, material is disappearing. Well, what if we're producing end parts? What we'd like to do is deliver those end parts to the customer. Now let's just consider one process here. And I want to deliver end good parts to that customer. Well, the question is, how many parts do I have to put through this process to create those end parts? Based upon the scrap rate, we're not going to consider rework at this point, we're going to end up with 1 minus S times X in terms of good parts. So now we can equate N equals 1 minus S times X and then solve for X. Here you can see that we will divide the number of parts that we need by 1 minus S. What is the meaning of 1 over 1 minus S? Well, you can think of that as for every good part, you actually make 1 over 1 minus S parts, which means this implies that 1 over 1 minus S is strictly greater than or equal to 1. Now, what happens when your scrap rate is 1? That means you can't produce any good parts, and so this becomes infinity. But this ratio will always be greater than or equal to 1. Obviously, you would like to get it as close to 1 as possible, which is the case when S is equal to 0. But that's not always possible depending upon the materials and the geometry that you are trying to create. You can also look at this from the point of view of a probability model. So if you think back to Stat 231, you could think of each part representing this independent Bernoulli trial. And that's essentially a coin toss, right? So we think of going through this process and then coming out the other side of the process. We have a certain probability of success and its potential for failure. And that failure ends up in scrap. Now, the number of parts until we have a success, as you know, is a geometric distribution. So if you go back and look up the geometric distribution, what you're essentially saying is the probability that you will have a certain number of successes, that's the number of parts that we want to produce, is based upon the probability of success raised to the n minus 1. In other words, we're going to have n minus 1 failures and then 1 success. So the question I have here is, what is P? If, again, P represents the probability of success. In our context, P will represent 1 minus S, S being the scrap rate. So this number here is strictly between 0 and 1. As S approaches 0, then our probability of success goes to 1. As S approaches 1, then our probability of success goes to 0. So when we think about that probability model, we're thinking about how many parts do we produce until we have a success. Based upon this geometric distribution, we have a value for P of 1 over 1 minus S, as we saw before. So we think about the expected value of N. What will you expect in your system? Well, in terms of the relationship to scrap rate, the mean of a geometric distribution, if you go back and look at that, the expected value corresponds to 1 over the probability of success. So that would be 1 over P. Well, 1 over 1 minus S is the average number of passes through the process until we have a successful part. Why? Because we said P is equal to 1 minus S. So again, the meaning of 1 over 1 minus S is Very important to your manufacturing system. It tells you essentially how many times you're going to have to produce a part until you get one good part. And we'll be seeing that through the rest of this semester. Now, what happens with rework? In rework, we've already said that we're trying to restore a part to its intended outcome in terms of the characteristics of that product. So the first question we have to ask ourselves is it possible to rework the product? Well, if we define R as the fraction of defective parts that can be reworked successfully, then we're going to have a number between 1 and 0. And we said in our material balance that we might have to add additional material. So M sub R will represent the average amount of material, because there could be some variation from part to part, that we might have to add during rework. So the key concepts here are, first of all, going into a process and exiting a process, we have a certain material balance that must be maintained. And that material balance involves a scrap rate, which characterizes the process in terms of its ability to achieve the intended outcomes. We also produce waste in this process, where material enters the waste stream. And finally, rework represents a secondary process in which we try to restore the value of that part to its intended outcome. So in summary, each individual process is going to transform material from some initial state coming into the process to a new state where we've performed some delta, which represents value that's being added. If we're not producing value, then that particular process is meaningless. When the part features do not satisfy our specifications, then we consider that part to be scrap. And then we have to make a decision. That decision may involve rework, where we restore the part feature to its intended characteristics, or we take that part and place it into the waste stream.